It's my great pleasure to introduce Anna Zaks and Jordan Rose. Both Anna and Jordan work on the static analyzer, and they are going to explain about how you can extend the static analyzer to find bugs that you're interested in finding.
Hi, I'm Anna.
I'm Jordan.
And we are both active contributors to the Clang Static Analyzer, and this is what we are going to talk about today. So first, as many of you know, the Clang Static Analyzer is a bug-finding tool, and it's part of the Clang family. So in this talk, we're first going to give you some brief overview of how it works behind the scenes, and then we are going to teach you all how to write your own custom checker that will allow you to check your own bugs. Okay, so let me start with some motivation first. So as many of you agree, warnings are great. They provide free, fast, and anonymous code reviews. They catch errors early in the development cycle. So here is an example of a Clang compiler warning that tells you this variable log handle is being used without being initialized first. So we all love our warnings. However, warnings have their limitations. So consider this slightly modified example where all the login routines have been put behind a flag. So it's very easy for a developer to make a mistake and reverse, for example, a condition within one of the if statements. This happens quite often. And notice that it would be very hard to write a compiler warning that would catch such a problem, even if you were to write a flow-sensitive warning. However, this is still something that could be found statically without running the program. So actually, if you run the Clang Static Analyzer on this code, it will warn that here the log handle variable is being used without it being initialized first. In addition, the Static Analyzer also is going to show you the path of how this problem could have occurred while running this routine. So it first tells you, OK, here you declare the variable log handle. You forgot to initialize it. Then it goes, evaluates the first if statement. Here it assumes that the write to log variable is set to 0. So the log handle is not being initialized. It evaluates the second if statement. Here it remembers that write to log is 0. So it's going to step into the if statement and use. Here you have your use of the uninitialized variable. So what makes static analysis good for finding issues like this? Well, it explores every pass through your program. It performs what's called path-sensitive, context-sensitive analysis. And this comes with a cost. The algorithm is exponential in the worst case, but it produces very precise results, and it allows us to find new bug categories. For example, use after freeze, leaks, etc., statically. So let's look at another example. Suppose you wanted to check Unix file APIs. Then one of the things you might want to check for is that if you that every pass through your program, if you open a file, you close the file on every pass through your program. So look at this example. So here we have a routine which writes a character to a log file. So you pass in the pointer to this character that you want to write. You open a file. You check if file fopened succeeded. If it succeeded, you check if the data pointer is null. If it's null, you return. Otherwise, you write the character to the log file. You close the file. You return. So the problem here is obviously is that we forgot to close the file on an early exit from the function. And this happens very often. This is a very common mistake. And this is a type of error that the static analyzer is very good at catching. So it's going to catch it and tell you, OK, this is the path on which the error could have happened. So what gives the static analysis its power? Well, static analysis uses this technique that's called symbolic execution. And what it does is it performs a path-sensitive walk over the Clang's control flow graph. And symbolic execution is very similar to regular program execution, but it's also different. So for example, when you just execute your program, you explore only one pass through this program. And this path is defined by the input values to your program. When you perform symbolic execution, you explore all paths through your program. And instead of using concrete values, you're going to use symbols. So for example, if a static analyzer is simulating a call to a function that it doesn't understand and it doesn't know what concrete value this function will return, it's going to conjure a new symbol and use that instead. Also, as the static analyzer explores those paths, it accumulates constraints on the symbolic values. And those constraints will allow it to know which paths are feasible, and it will also let it know what is the set of values each symbol represents. So And essentially what the static analyzer does is it builds a graph of reachable program states. So let's look at this example. This is the example from before, and I'm going to give you some intuition of how this graph looks by actually building it. So it starts from the beginning. We enter the function. We see this variable data. So the static analyzer doesn't know what concrete value it will have. So it conjures a symbol D and says, OK, we'll represent pointer data with a symbol D. Then it goes ahead and it evaluates fopen. Again, it doesn't know what fopen will return, so it conjures another symbol F to represent the file handle. It continues. Now it's already, it executes the if statement. And here it realizes that you have to split the path. So we actually want to explore the path on which the condition evaluated to true. And we also want to explore the path on which the condition evaluated to false. So we branch the path. And in order to record the fact that we actually branched, we are going to store constraints on the symbol F. So on one side, when the condition was false, we are going to say, on this side, symbol F is constrained to be 0. And on the other side, we're going to say, OK, here, symbol F is constrained to not to be 0. Let's keep going. So here on the false branch, if you keep executing, we reach a return. Here, the analyzer realizes that it reached the end of the path and stops. Then still there is one node that it hasn't explored fully yet, so it goes back there, simulates the if statement, and here again it branches because two possibilities exist. And notice here that we propagate the constraint on the symbol F, and we also record the fact about the split with adding additional constraints on the symbol D. OK, let's keep executing or simulating the execution. Now it simulates fput-c, simulates file close, hits return. And now there is only one node that hasn't been explored yet fully, goes there, hits return as well. So this is our graph of reachable program states. And like if you look at it, it's kind of interesting. Like this is how the static analyzer works, but it doesn't answer our question. What we're really interested in here is that do we have a resource leak or not, right? So in order to make this useful, we are going to add some extra information, domain-specific information to the graph. So we are going to give this red token to every state in which the file is open. So now, in order to answer our question, find the leak, we just need to find a node in which the file is open and we reach the end of path. It's like very simple. So essentially, the static analyzer finds a bug by solving a graph reachability problem. So let's zoom in on each node. So each node consists of a program point and a program state. Program points tells us where in the execution we are. It has execution location that tells us, are we just before simulating a particular statement? Are we just after simulating a particular statement? Are we entering a call, etc.? It also has an abstract stack frame that lets us reason about interprocedural analysis. In addition, we have program state. Now, program state has an environment, and this is a map from Clang expressions to the static analyzer values. We have a store that represents stack and heap memory. We have constraints on symbolic values, and we have this data structure that's called generic data map. And it essentially allows you to store opaque data into the program state. So all the checkers are going to use generic data map to store their own information inside the program state. So let's talk a little bit about the checkers. Checkers are actually active participants in the graph construction. So this is how the graph construction could have happened. The analyzer core generates a couple nodes, then the checker 1 generates a node, checker 2 generates 2 nodes, and it goes on and on. In addition, a checker can actually tell the analyzer core to stop the graph exploration. So if it finds a really nasty bug, it can tell it to stop by generating a sync node. And for example, if you're writing a null pointer dereference checker, it doesn't make to keep simulating this path after a null pointer dereference happens. So we should just stop. So how does the analyzer core knows when to transfer control to each checker? Very simple. Checkers implement the visitor pattern. So for example, if a checker is interested in an event right before a return statement is processed, it can register for check pre-statement on the return statement. If a checker is interested in to be involved right after a call has been simulated, it can register for check post-call. If a checker is interested in a binding of a value to a location, and binding is just another name for a store, it can register for check bind. And there's a whole bunch of other callbacks that checkers can use. And we have this checker developer manual page that has a link to a Doxygen page that lists all of the visitors, all of the callbacks you can implement. OK, so by now I hope you all have some intuition about how the analyzer works behind the scenes. So we are going to dive into the code, and we are going to write a Unix Stream API checker. That will be the same checker that I used in the introduction earlier, the one that found the resource leak. And Jordan is going to help me with that.
OK, so everyone here is familiar with the common Unix file stream APIs, fopen, fclose, and if you open a file, you had better remember to close it, or your program's in trouble. And so what we want to do is figure out how to represent these possible states of opened and closed in the analyzer and put it into the program state so that we can find out when bugs occur. And so to start off, we just want to talk about what are the possible states for a file handle. We have this untracked state before anything actually happens. We have the open state, and then we have the closed state that all file handles should end up in. And the important thing to notice here is that the API calls are what drive the transitions between these states. So when I call fopen, that's what causes the file handle to become opened. When I call fclose, that's what causes it to transition to the closed state. So we're going to build up this state diagram in these transitions and use that to find two kinds of bugs today. And both of them are based around the idea that when you open a file, you have to close it exactly once. So the first kind of bug that we're going to find today is when you close the file more than once. So if you call fclose on a file that is already in the closed state, then we should report an issue. The second kind of possibility here is that you forget to close a file, and we're going to call that a general resource leak. And so in this case, we have a file that's in the open state, and we lose all references to it, so we know that you've forgotten to close it. And we should report this bug as well. Now, in order to report these two bugs, we're going to break this down into a series of several different steps. The first thing we want to do is just define these three states, untracked, opened, and closed, in such a way that we can actually put them into the program state and the analyzer core. So we'll start off with just a simple type-safe enum struct here. This is a very common pattern in C++. So we have this struct called streamState. And inside it is just an enum representing whether the stream is opened or closed. And this is the bare minimum of a type-safe enum, but it's not quite enough to actually put this into a program state. In order to do that, you have to implement two more methods, operator equals and the profile method. Now, operator equals is the same comparison operator any C++ programmer is familiar with. Are these two stream states the same? The profile method is LLVM's equivalent of a hash function. And the reason these two are important is because when you ask if two program states represent the same actual execution state, you need to be sure to take actual checker information into account. So this is what we need in order to represent stream states in the program state. But just to make things easier and a little clearer on the following slides, we're going to add some convenience accesses as well. So this is what you'll see on most of the following slides. OK, now that we've defined this structure, what we want to do is figure out how to put it into the program state. And we're going to want a map from each file handle to its current stream state. When we update the map, we'll do it by calling the set method on a state. And it's very simple here. We pass it the file handle and its new state of opened, and that updates the state. And you'll notice that we are assigning the results of the set method back into the variable. Remember that Anna said that we're building up a graph of states. This means that all states have to be persistent. So rather than modifying or mutating the state, the set method is going to return an updated state with the new map value recorded. After we set values into the state, we're going to want to get them out again later. That's using the get method. And here you'll notice it returns a pointer. This could be one of two things. Either it's going to be a valid stream state representing an opened or closed file handle, or it's going to be null, meaning that this file handle wasn't found in the map. This is how we're going to represent the untracked state that we mentioned on the original state transition diagram. So we don't have to do any extra work to support that. Finally, when you use one of these maps, you have to make sure to register it with the program state ahead of time. And for that, we have this nice macro, register map with program state. Underneath this is a whole bunch of template metaprogramming goop that you should not have to worry about. All you need to know here is that we are creating a new map called stream map from symbols representing file handles to this stream state struct that we defined on the previous slide. So that's all it takes to add your own custom information to the program state. And what we have to do now is start adding these state transitions so that we can actually eventually catch the bugs. So the first one we're going to add is the one for fopen, which is the first thing any user will do in their program. And to do that, we have to start implementing our checker proper. So here we have this class, Simple Stream Checker. And Simple Stream Checker inherits from this checker template. And the arguments to the checker template represent the callbacks that your checker is interested in. So in this case, we're registering for a post-call callback, which means after the analyzer has finished evaluating a call. And if you take a look at the signature of post-call, you'll notice something funny here. We have some reasonable arguments of an abstract representation of the call and then the context of what else is going on in the world at the time. But you'll notice that it's const. And this is because checkers are stateless. The order in which checker callbacks happen is not guaranteed by the analyzer as it explores the different branches in the graph. So if you want something to persist from one node to the next, you have to put it in the program state. And so all checker callbacks are const, just to remind you of this. What's in this check post call callback? Well, the first thing we should do is say, are we actually calling fopen? And if not, we shouldn't waste any more of the analyzer's time. If we are, though, then we want to go ahead and get the return value from that fopen so that we can start tracking it. And what is this get return value going to return? I mean, we're simulating the program, so we don't have an actual file handle here. And so whenever you ask for the value of something in the analyzer, what you get back is called an sval. And this represents any sort of value the analyzer can reason about. Maybe it's a concrete integer or the address of some variable or a symbolic value. But the important thing to note is that svals are transient. The sval that you get returned from fopen might not match the one that's eventually passed to fclose. So this isn't a suitable way to represent file handles in our map. So what are we going to do about this? If we go back to the code here, we see that it's calling getAsSymbol on our sval. And what this does is it looks inside the symbol, inside the sval, and tries to extract the symbol that the analyzer will create. Recall that what Anna said, that the analyzer doesn't know what fopen is going to return, and so it conjures a symbol to represent that return value. We're going to take advantage of this to use the symbol to represent the file handle in our map, in our stream map. So once we have this symbol, it becomes very easy. All we have to do is get the state out of the checker context, update it by saying this file handle is now open, and remember to store it back into the state variable, and then call this add transition method in order to add this state to the graph that we're constructing. That's the callback for fopen. The entire thing fits on one slide, and that's basically 90% of writing a checker, finding out which callback to implement, and then adding the proper transitions in the state. So fclose, naturally, is going to look very similar. We start off again by saying which callback would we like to implement. This time, we're going to use a pre-call callback so that we can check the arguments before we actually evaluate, the analyzer core evaluates the call. Same as before, we start off by asking if this is actually a call to fclose. And additionally, we do a bit of defensive programming to make sure that there is an argument being passed. Once again, we want to get the value of that argument and the symbol inside it. This time, instead of get return value, we use get arg sval. But it's the same idea. Finally, we get the state out of the checker context, update it to say this file handle is now closed, and store it back and add it to the graph using add transition. Basically the same thing as you just saw before. And with that, we've actually defined all the states and state transitions for a program that's properly using fopen and fclose. That means it's time to find some bugs. So in order to handle this double close case, let's go back to our pre-call check for fclose. And this is the exact same code that we just saw before. So I'm going to let you pause and just read it to get it in your minds. I'm going to fold up the first two paragraphs here just to make a little more space. And what we basically want to do here is before doing this update the state part, we want to get the current state of this stream and say, has it already been closed? And here's some code that does exactly that. We call the get method with this file handle symbol. And remember that we get back a pointer. So first we check, is this a file handle that we are tracking? And then if it is it a file handle that's already been closed? If both of these are true, then we have a problem, and we need to report an error. The first step in reporting an error in the analyzer is generating a new node. But this time, if you double close a file, your program is actually going to crash. And that means it doesn't make sense for the analyzer to keep simulating after this point. So we're going to call generate sync instead of add transition. This will stop the analyzer from continuing to explore this path. Now, there is one caveat here, which is that it's possible that the double close bug could have happened along another path through the program already. And in this case, generate sync will return null. But if this is the case, we've also already emitted a bug report, and we don't need to do that again. So we'll just return. But let's say this is the first time we've seen the double close, and then we need to actually tell the user about it. To do this, we create a new bug report. We give it our bug type, which just says what kind of bug it is, a custom error message to display, and the node at which the bug occurred, which is what allows the analyzer to draw the path that shows exactly how this happened. We add some extra information to make the report a little nicer, giving it a range to highlight in the report it's going to show to the user, and also saying that this file descriptor symbol is interesting, meaning that maybe the diagnostic machinery should pay more attention to it when choosing which parts of the path to omit. Finally, we hand the report off to the checker context to do all the dirty work. That's all it takes to implement a bug, a check for a bug. So let's run this and see if we can actually find a double close error. Here we have a case where somebody tries to write to a file, but they do an early return if there's no data, and they don't quite get it right. And indeed, running the checker that we just wrote, we find this error. You can even see on that last line there that the call to fclose is highlighted within the line, thanks to our call to add range. And just like any other analyzer report, you can open this up and get the path on which this error occurred. So we've just implemented our first static analyzer check from scratch. And this can find real bugs in real production code. But there's one more kind of error that we promised we'd do today, and that's the case of reporting an error on a leak. And this one's a little bit different. So Anna, can you do this one?
Yes, I'm going to do that one. So as Jordan mentioned earlier, we report a leak if a file was closed, and then we lose reference to that. This was a symbol that represents the file handle. So how do we know when we lose the reference to the symbol? Well, the static analyzer has this very convenient callback that's called check dead symbols. So we say that a symbol is dead if it will no longer be referenced along the path. And whenever a symbol dies, whoever registered for this callback will be notified. So let's go back and implement the callback. So first we get the state from the checker context, so it will just tell us where in the execution we are. And then what this callback is going to do first is it's going to populate a vector of leaked streams. So we just want to collect all the symbols that have been leaked at this point. So in order to do that, we are going to ask the state to get us back the stream map. So the stream map will have all the symbols and their state for all the symbols that we are tracking. We are going to iterate through all of the tracked symbols, and we are going to check if they are dead or not. So in order to check if a symbol is dead, we just ask this object, symbol reaper, is the symbol dead, and it will tell us. Next, we check if the symbol is dead, then we add it to the vector. So let's zoom in on the is leaked definition. How do we know if the symbol is dead? Well, if it's leaked, well, if it is dead and the file is opened, then the symbol is leaked. Very simple. So we are coming back now to the code I showed before. So now we have all the code that's needed to get the list of leaked symbols. After that, all we need to do is generate a node and call this as auxiliary routine that's going to report all the leaks we found now, and it's going to associate them with that given node. And the routine is very similar to what Jordan presented. What's interesting here is that we are not generating a sync node. We are generating a regular node. And the reason is that leak is not a very bad bug. So it's not a fatal bug. So we actually do want the analyzer to keep executing along this path, just in case it will find some more serious bug. In addition, one thing that we also have to not to forget is that if a symbol died, it means that we will no longer see it along this path. So we should not keep the stream checker information stored in the state for a dead symbol. So we just have to make sure we clear out the state so that the program state stays lean. Okay, so let's test our leak finding code. Okay, so I have a very simple test case here. We open a file, we write to the file, we don't close the file. We report a leak, and we even show the path. Okay, seems that we are all done.
Anna, that wasn't a very good test case. I mean, it was tiny. Are you really sure that worked?
Okay, just to make Jordan happy, let's run our test case that I presented earlier in the beginning of the talk. So, okay, here okay. So to my defense, we do report the first leak as expected on the early return from the function, but we actually report another leak here, and that's unexpected. That's actually a false positive. And let's see what happens here. So what happens here is that we open a file, we report a leak in a situation where we open a file, fopen returns null, which means the file is not open, fopen failed, and then the analyzer still expects the code to close the file, and that's not what the user, whoever wrote this code expects. So let's go back to our recipe and see what was wrong here. Okay, we can fix this by saying we will only report a leak if a file is open, we lose reference to the symbol, and if we know that fopen succeeded. So let's go back to the, okay, so let's figure out how we can do that. Remember I said that in the beginning of the talk that we have this convenient pre-statement callback, so maybe we'll register for pre-statement callback for an if statement, right? And then we check, oh, if f is not equal to null, then we know that the file is not, opened. Well, we'll also have to handle this case. And someone could have written like this in the while loop. And actually, the possibilities are endless. So what we actually want to check is we need to know if a symbol is constrained to be null. So how do we do that? Let's go back to our leak definition and refine it. So this is what we had before. We reported a leak if a symbol was dead and a file was open. The way we are going to change it is we are going to go and ask the state to get us a constraint manager. If you recall the beginning of the presentation, I said that the analyzer keeps track of all the constraints. So constraint manager is the one who knows all about those constraints. So we are going to get the constraint manager, and we are going to ask it, is the given symbol null in the given state? And it returns this value. And notice that the value is not a Boolean, it's a tri-state. So it can say, either it is true, yes, the symbol is null at the given state, and this corresponds to the case where fopen failed, or it is false, it knows that it is false, the symbol is not null in the state, fopen succeeded, or it might just not know. And this would correspond to a case when the user just didn't have this check, so the analyzer just doesn't know which one is true. So we are only going to report a leak if the symbol is dead, if the file was opened, and if we know that open failed is not constrained to be true. So it will be in both cases, either fopen succeeded, or the user didn't check. OK, let's go and rerun it in real life on our example. And here we go. We don't have the false positive anymore. We did it.
So there are a number of things that we didn't get to talk about today just because of time. And the first of these is just checker registration. This is just a few lines of boilerplate for each checker. It's very easy. You can see all the checkers doing it in the Clang repository. There are many ways in which the diagnostics could still be improved, such as telling you the name of the file handle that you tried to close twice. This particular checker doesn't currently handle relinquishing ownership, which is a case where you open a file, but you expect another function to close it for you. Or you open a file and you put it into long-term storage to be closed at the end of the program. This checker won't handle that. Finally, we didn't cover what it takes to write a good set of regression tests. All we showed you is that if you don't test, you're likely to have both false negatives and false positives. So for more information and to see the full version of this checker, you can look in the Clang source repository, and where we have both the checker that you see here today, along with the tests that we've used to qualify it.
So let me talk a little bit about the limitations of the current implementation of the analyzer core. The constraint solver that we are using is limited. So for example, it doesn't reason about the bitwise operations. The constraints involving multiple symbols are not represented. We do have some interprocedural analysis, but we only reason about one translation unit at a time. So we don't have whole program analysis. Of course, the analyzer is only good as its checkers. And even though we have some of the checkers implemented, contributions are welcome. To summarize, we presented the static analyzer that performs a symbolic path-sensitive execution of your program. It is extendable with custom checkers, and it provides very comprehensive diagnostics. And we support two diagnostic outputs. It's plist and HTML. All the screenshots we presented today were screenshots of Xcode, and Xcode uses plist. HTML is not as polished, but it could be improved. What I didn't mention today as well is that it is possible to write syntactic or AST-based checkers and add them to the analyzer. So if you have some stylistic checker or a code complexity checker idea that you have, and it doesn't really fit into the Clang compiler, you could consider extending the static analyzer with it. For more information, go to the Static Analyzer website and send your questions to CFE dev mailing list. We check it all the time, and we'll answer your questions almost instantaneously. OK. Now, I see we've used up the first 35 minutes, so we know what you're all going to do in the next 23 hours and 25 minutes.
Any questions?
Let's first thank our speakers. So before we go into Q&A, I forgot to have an announcement. All of you were passed out surveys to record what talk you enjoyed the most out of the day. This is actually pretty important. Please turn these in after the talk. It's going to be tallied up before dinner. So with that, please, any questions? If you have any questions, please try and use the microphone.
No questions? Everything was clear? OK, I hope there will be lots of patches coming in. Oh, maybe there are questions. Uh-oh.
Yeah.
Okay.
For warnings that are, is this on? Yes. For warnings that are not program state dependent, how do you decide if it should be in the main compiler in Clang or if it should be in Analyzer?
So it's kind of it's kind of a hard decision, right? I think I guess there are two. I don't know. I think it's like one of the policies is basically defined by a compiler, right? Like if compiler. Sometimes the warning is not good for a compiler. For example, it has a too high of a false positive rate. Then the static analyzer allows, like, I think it allows you to have some.
I mean, that's that. The other thing too is the compiler we tend to not embed a whole bunch of domain-specific knowledge into, right? So, I mean, for very common used APIs like printf, those are also part of the language standard. Embedding that knowledge into the compiler makes a whole lot of sense. Embedding knowledge about like some specific APIs about Chrome, for example, that wouldn't make a whole lot of sense in the compiler unless you were building your own custom version of Clang to build, your executable. That wouldn't make sense for a lot of other people. So it's a great place to kind of put a lot of more domain-specific reasoning. And also it can be far more expensive. So it could still be a syntactic check. It still could be pretty fast, but maybe too cost prohibitive as a compiler warning.
Thanks.
What kind of scaling issues do you see with these tools? And for example, did you try some large code bases in whole program mode with it?
Sorry, so you're saying like how well it scales?
Yes.
So
what problems with scaling do you see?
What
if
problem
any?
with scaling we face? I don't hear. Like, can you repeat the question?
Yeah. If you apply it to a large code base, how slow it is?
So like as I mentioned previously, we only do like one translation unit at a time. So this actually allows us to be more scalable. So like if you have the algorithm is exponential. So if you have one humongous file, then it's going to be, you'll pay the price there. But actually it scales pretty well. So for example, SQLite is one file, and like we process it within like, I think it's in under half an hour. Then actually like we ran it on LLVM, for example, and
That takes about an hour.
that takes about. So the scalability is not a problem as long as we don't deal with whole program analysis.
Are there any remaining problems with C++ support?
Jordan.
So the C++ support has come a long way this year. I would say that so there are some things that are just features that are still not completely implemented. So the most important thing that's probably still prohibitive right now is that constructors and destructors for non-trivial types are not inlined, and not because we are not able to model them, but because we found that the diagnostics that they produce are overly confusing and don't always point to the real source of the problem. So things are turned off right now in order to minimize even true positives, but positives that the user may not be able to fix. We'd like to improve this.
While file handles have like value semantics, we have pointers in C and C++. How do we handle those?
How do you
So in general, the analyzer actually handles modeling of memory very well. If you malloc a whole chunk of memory and store file handles into it, it will track which parts of that malloc memory are refer to which file handles, and you can pass that around to different functions within the translation unit, and it will assume that. Now, if you have pointers coming from another translation unit or from the symbolic inputs to your top-level function call, that's a little harder, and so we do some basic analysis to sort of guess at what these pointers may or may not alias. Unlike the Dan's talk that you may have seen earlier, it's okay if we maybe get an alias guess wrong.
So you have the constraint manager or the constraint solver. How much does it know about built-in functions? Does it know anything about fopen in the sense that, for instance, it doesn't return the address of another function, or does it just look at paths that have been taken inside of this function?
So the constraint manager is something that just keeps track. So we have like symbols, and this just keeps track of ranges that each symbol can have, like ranges of concrete values that the symbol can have. All the domain-specific knowledge, for example, for fopen, it's all modeled by checkers. So there is a very clear separation of what the checkers can reason about and what the core reasons. So core has no notion of like domain-specific knowledge.
Okay, thanks.
So in your example, you used two different types of visitors for the calls. You used a pre and a post. I was just curious what exactly happens in between those two, and when would you want to use one versus the other?
I mean, that very much depends on your use case. A lot of times the general idea is if you care about the result of a call, you would use post-call, and if you care about the arguments, you would use pre-call, even though you can check the arguments during a post-call check. It's just sort of the conceptual separation. What the analyzer is doing in between the pre and post checks is attempting to evaluate the function in one of several ways. It's possible that this function is something that the analyzer is within the same translation unit, and so the analyzer can actually attempt to model that function precisely. It's possible the function is an extern function and we don't have anything for it, in which case you mostly just get a conjuring of a return value and invalidation of the arguments. And it's also possible that some checker can actually volunteer and say, I know how to evaluate this function better than the analyzer core. And for fopen, we don't want to do that because we don't want to have to model error no and all the other possible things it could do. So, but we do want to take special handling of the return value. And likewise for fclose, we don't care so much about the return value in this case, but we do care about the arguments.
A more general way I would look at it is pre-visit is for checking preconditions, and post-visit is for checking post-conditions after the call is evaluated.
All right, thanks.
Have you compared the quality of results with commercially available checkers like from Coverity?
We haven't, I don't think we directly compared the quality of results. I think in comparison to Coverity, we are not as mature. However, we have much more domain knowledge for Objective-C, for example, which Coverity doesn't. So they, right, I think that's...
I mean, the Clang Static Analyzer was originally developed for Apple platforms and for OS X and iOS programmers. And so there's a lot of domain-specific knowledge specific to that. It's only recently gotten, I mean, it's always been fairly general powerful, but it's only recently that the domain-specific knowledge in other areas has also increased, and the increased C++ support. So there are definitely things that Coverity can do that we can't yet, but we'd like to think that there are still things that we have that make the analyzer a better tool for certain projects. In addition, because it's doing a different sort of analysis, it's possible that the analyzer will be able to provide more precise results in a particular case and with faster turnaround.
I'll add that I've seen it find bugs that Prevent has not. So
That's true, yes.
it's not a strict superset of each other.
Okay. Thank you all for coming.
Thank you.